All right, so in this video, we are going to look at an example of operational semantics in CoQ. So we have some boilerplate code that we are going to use in this example, but there are a couple of things that I want to draw your attention to. So if you've seen the example from the previous weeks of the course, you'll see that syntactically this program is very close to what we had in the previous weeks, with the exception of the repeat operation being replaced by while loop. So looking at the syntax, it is still taking an E and a body, which is a program, and it's evaluating it. But the thing that is different here is the semantics that we are going to assign to this operation. So here we assign some syntax so that we can execute this program. And then we are going to look at this small step operational semantics steps that we have defined here. There's a total of 7 rules here, which is the same number that we also have on the slides from the course. So let's consider this particular rule called step while true. A good way of thinking about this is to think about it in terms of a reason where we have something that is given to us, and then a fact that we can know given that prerequisite or that precondition. So here, what we are saying is if we have a variable called E in our valuation, which is our memory, and in this valuation, E doesn't evaluate to 0, then we know that if we have this situation here, this condition here, where we have a valuation and a while program with E and a body, that would step into another valuation with a sequence and a body and another while loop that has to run on that E and that body. So as you see, it's easy to translate long horizontal line definitions to CoQ and vice versa. And here we have utilized this. So now let's move on to a version of the factorial program. But this time our implementation uses a while loop. Okay, so let's consider this. We are taking an input to a global variable called input and storing it into n. And we are initializing our accumulator as 1. We will loop as long as n is not 0. And every time we are looping, we multiply our accumulator by n and decrement our n by 1. And unlike the old example provided in course material from 2 weeks ago, this particular line is a requirement for our program to terminate. And then after we're out of this while loop and we're done with this while loop, whatever was in our accumulator is stored in a global variable called output, and that's the equivalent of returning. And we're done. So here we have a concrete program, and we are going to demonstrate the execution of this program. So let's go ahead and do that. And the way we are going to do this is we are saying for all possible memories, the only thing we know is that if we do a lookup on input, the variable input on our memory, it is going to be set as 4. If we have this guarantee that every time we look up our memory for the value of input is the number 4, then there exists a memory. So there is a memory, and if we recursively step through our program, starting from our beginning memory using this factorial definition, we are going to eventually end up in another memory with skip, which is something we cannot step from. That's essentially the end of the program. And there's a conjunction here. So this fact would be true. And in addition, there is going to be another fact that is going to be true, and that is that if you look up in that memory the variable output, it will evaluate to the number 24. So let's go ahead and actually prove this. So when we begin this proof, we see that there is an implication with V1 and another fact that we want to hold on to, this hypothesis. And if this is the first time you're seeing this keyword example is just another synonym for lemma. It's just another way of naming the same thing. So since we are trying to prove a concrete implementation of a program, we do not need to use induction to do so. Instead, we are just going to do model checking here. And basically what we are going to do is take a number of steps in this program and using these operational semantics, show that our program adheres to those. So currently, what CoQ is asking us to do is to predict the final memory in the program. And we know that that is going to be there. We know that that actually exists. We can show that it exists. So we are going to go ahead and claim that there exists such a memory when we are done. Basically, we told CoQ that we are sure that it would become clear later what this memory is going to be. Allow us for now, though, to take a step towards this proof. Now we have to show that we take a number of steps towards this memory skip. And in this memory skip, the variable output evaluates to 24. So we make a decision to prove each side of the conjunction separately. And to do that, we are going to use split. And we are going to go in the first case. And we are going to unfold the factorial program in this case. So notice the program has three parts. There's this part before the loop, where we are setting our variables. Then we have the body of the loop. And then finally, the last part of the program before it sets the variable output and exits. And sometimes it is better to look at this program without the notations on. So we are going to turn that off and look at the program. So the top ASC node is actually this sequence statement. Left-hand side of that node, which contains our initialization code and our while loop code, is this sequence. Actually, this sequence over here. And this is the right-hand side child of the sequence. And then we have another sequence here, who in its left side has two assignments, coincidentally another sequence in there. And then on the right-hand side, we have these while loop and all of its own assignments. So looking at our operational semantics to see which one we can apply to the sequence, the two operations that allow us to make a step or could allow us to make a step here are the ones that have sequence in them. The second one that has the word done in it is only used when the left-hand side is skipped. In other words, we're basically done. But if you can take a step here on the left-hand side, we should use this first one, which is step seek L done. And that is the one we're going to use here. And we are going to do that by applying this step here. But that doesn't work. And then looking at our goal, we see that we forgot something here, and that was that we wanted to prove TRC step. That's our top level goal. And just to make sure that this is applied correctly, we are going to apply TRC front, which is the kind of TRC step that applies here, that allows us to make a step forward. And the reason we had to use eApply instead of applying TRC front was that the definition of TRC talks about the fact that we can step from X to Y and then from Y to Z, and therefore we can go from X to Z. And apply is just not a tactic that can prove that. E-apply will try to prove that chains of implications that we are going to use here. So it allows us to apply TRC front here. Now notice this gives us two goals to prove. The first one is just a single step. And it lands us over here. The second goal is where we pick up after that one step and the rest of the steps. So now applying step seek else step, notice we lose one of the sequence commands that we had. All right. We end up with another AST that has a sequence as its top node. And we are not done. We don't see a skip here. So really, the only tactic we can still use is this step seek else step. So we are going to reuse that. And then we have a sequence again. We are going to apply this tactic again one more time. And then we have one more sequence up here. So stepping one more time. Now, finally, we don't have a sequence. So what are we left with here? And we want to prove a step with this assignment statement. And there is a rule for that. It's called step assign. It's up here. We saw it. So we're just going to apply that as well. And because we decided to write our version of assignment exactly like the way it is on the slides, we are left with a situation where CoQ is asking us to prove that the left-hand side of the equality is equal to the right-hand side. But what we can do here, and CoQ allows us to do that, is to just say reflexivity. And CoQ buys it from us that the two sides are equal and takes away that goal from us. So notice, after all that we've done so far, we went from this first part of our program taking a step, now being a skip. That's just like the first part of our program that we analyzed. And we had to put in quite a bit of tactics just to get here. This was just to execute the first assignment statement on the first line. And technically, we are not even done because we still have to get rid of the skip here. And now if we take 3 more steps, and basically if we copied these and pasted them here, for the first time, we have a sequence whose left-hand side is a skip. And that allows us to, for the first time, apply step seek L done. And that finally gets us to a program which is missing its first assignment statement. So that is 20 lines in CoQ just to execute one line of actual code. So let's change our strategy here and do something that's more economical. Behold the next 140 lines of proof. So starting at 288, our proof ends at 428. All right. So instead, what can we do here? So a way to solve this, since everything is very repetitive, is to create a LTAC. The course staff here have called it step easy. And it will repeatedly apply one of these tactics or sequences of tactics, and then follow it by CBN, which is the same as simple. Notice these are all the constructors of the operational semantics that don't enter a loop. Because in this case, if we were to prove stuff about entering the loop, we would need human intervention. So we're going to use these over and over again. So here's another version of our proof. So now every time we want to take a step, we call step easy. It takes an entire step for us and allows us to go through the proof faster. Still, there are quite a few lines of code, but there's still a bit of repetition going on. So that reduces the number of steps we have to take. But hey, we can define even more LTACs here. So let's maybe do that. So this tactic here handles multiple steps for us by using the TRC front constructor and then calling the step easy tactic, which we defined, where the first step is proven using the step easy tactic. And then the second tactic here attempts to enter the loop using step left. So now with this toolkit, every time we want to make a step, we call TRC easy, but then in parts of our proof, we need to call TRC easy multiple times, but TRC easy cannot enter into a loop. So every time we get to a loop, we call TRC enter loop. We just need to do this a few times, and that gets us a very short proof. So using this machinery, here we are able to prove that this program we had, which was called factorial 4, was able to be, no matter on what memory we initialize it, if for that memory, the variable input evaluated to the number 4, after execution of our program, the variable output would be set to number 23.